I'd like to welcome Sunil Doddi as our program speaker today. Sunil is one of the newer members of the ISA Philadelphia board section. He's a certified automation professional, a certified functional safety expert, and a cybersecurity fundamental specialist. Sunil has a lot of credentials, and I met him here earlier this year. I think you're really going to enjoy what he has to say, and you're going to get a lot out of it. Sunil is also a certified automation professional, a CAP, as we call it in ISA. So, Sunil, welcome. Welcome to ISA Philadelphia. Welcome as program speaker. So, sir, I'm going to stop sharing my screen and turn it over to you.
Wonderful. Thanks, Jeff. I appreciate it. Arranging this meeting. I hope everybody will enjoy it. Whatever my perspectives, I'm going to bring it. Yeah. People who don't know me, my name is Sunil Doddi. Now I've been working in process and controls field 20 years, and I have ISA CAP and XCDA certified functional safety expert, and I say cybersecurity fundamental specialist. I also recently participated as an ISA CAP exam job task panelist. We have revised this syllabus for the CAP exam. So, that's a little bit about me. And let's get into the presentation. So the presentation is about, how to address automation safety properly in process industries. I try to focus on safety. It doesn't mean that, I'm ignoring security. Security is also very important. But in my view, security is a subset of safety, especially in our process industries, because you can the risk receptors are the business reputations and equipment. Even if you have if you get damage down, you can recover. But if a personal get injured or or a death happen, so then it's a big of an issue. So that's why in process industries, in my view, the safety should be more focused. So that's why it is called a comprehensive automation safety. So go to the next slide. Okay, this is about me. See that one. So what is the objective of this presentation is, learn about functional safety and cybersecurity and what they mean in our industrial control system, especially in the process industries, and learn different types of failures and types of threats, security threats, and learn how we can address the related standards, how we try to address these standards to implement properly. So first of all, what is automation? ISA defines automation as a creation and application of technology to monitor and control the production and delivery of products and services. So that is the definition of automation. So in other words, in simpler words to understand, it includes the field instruments and the control room equipment. Overall the control function. So that's the definition of automation. So ISCS versus ICS, from ISA 62443, which is a cybersecurity standard from ISA. An industrial automation and control system is a collection of processes, personnel, hardware, and software that can affect or influence the safe, security, and reliable operation of an industrial process. That is the definition of ICS. But I never seen anybody using ICS. Everybody, we all know it's the ICS, industrial control system. It's a general word that we use. That's why I try to use the same word in the total presentation. But it means the automation and the process instruments and also the control room equipment. So safety and security. ISC safety can be comprehensively, we can say, functional safety. And also cyber security. As I said, the security is a subset of safety. So the primary objective is to be safe. That's the primary objective. That's why we bring also the security aspect into it, because we want to be functionally is in a safety. So what is functional safety? It is a system or piece of equipment that depends on automatic protection and operates correctly in response to its input feedback or failure in a predictable manner. This is a functional safety definition. ISA in IEC 61511 standard is slightly different version of definition, but for me, you need to, for me, it feels like, you need to specify, a little more details about it, like, the feedback and the failure and, how the predictable manner and fail-safe actions happen. So what is cybersecurity? There is no definition or, a description what is cybersecurity in any of the ISA standard, So cybersecurity can be broadly categorized as an integration of cyber safety and physical security. So in our world, in our process industry, in our ICS world, cybersecurity implies, it does not imply that just an internet connection. It's something more than that, something beyond just an internet connection. So functional safety and cybersecurity used to be considered separate until 2016. They were not really integrated into any of the standards. Since 2016, IEC standards brought in cyber safety aspect into it to address to integrate properly into functional safety. So now both are together. They're all integrated, both cyber security and functional safety. So cyber risk assessment is required for our ISC 61511 Part 1 by clause 8.2.4. So that means if you want to meet the 6151 standard, you have to perform a cyber risk assessment also on the safety system. So, as we looked in previous slides, just now it is a integration between functional safety and ISC cyber security. So that is when we meet both functions, then only we can call ICS safety is properly addressed. You cannot simply focus on safety, and also you cannot simply focus on security. You need to bring both together to make the safety system safer. So the types of failures. Before understanding ICS safety comprehensively, we need to understand what are the failures and threats. The functional safety failures normally come from hardware failures and systematic errors. Hardware failures, also known as random failures, they come from field sensors, converters, the 4 to 20 milliampere transmitters, and I/O cord relays, CPU, everything. What are systematic errors? Systematic errors are design faults, that could rise from documentation errors at the, wrong specifications, or operational procedures, manufacturing process. These are all called systematic errors. So you can also say hardware failures are also systematic errors, because why would a hardware failure happen in the first place? There was something wrong, design. You can also call it a systematic error, but however, they should be separate. You can't treat them as the same failures unless you make sure the design the design changed, and also that eliminated the hardware failure. So both failures are completely different. They're not the same. So what are cyber threats? Cyber threats can be external or internal, and can be also categorized as deliberate and or accidental. Typical external threats are hackers, professional, amateur, or script kiddies, rival business competitors, nation states. These are the typical external threats. Typical internal threats are erroneous actions, inappropriate behavior by a employee, or inside threats. So safety and security, how they both are interlinked. So both actually depends on exactly the same three processes. You perform a risk analysis on it, whether it's safety or security, and then you implement or address how your risk analysis outcome, and keep on maintenance and improving. Both safety and security depend on the same life cycles. So what are the safety related standards? Governments and industry organizations are developing safety and security guidelines to help the industry, and they do a lot of recommendations there. For functional safety, we have ANSI IEC 61511, which is also IEC 61511. ISA adopted this IEC 61511. So that's why it is all one standard now. So it has three parts. And part one is about a framework, definition, system, hardware and application programming requirements. Part two is about guidelines on application of part one. Part three is a guidance for the determination of safety integrity levels. And cyber related standards. For cybersecurity, we have IEC 62443 series of standards. These are very good standards, very detailed out, and they did their best to put in a layman words, if I can say, and it's very, very good standards they have. So part one is general, and part two is for policies and procedures. Part three for system, and part four is component level. So this is the website link where you can see these nicely written, beautiful standards. So some, we're talking about process industry, but I also want to say, there are some other standards available specific to their own sector-specific guidances. Like API got a API 1164, ChemITC got a chemical sector cybersecurity, and for water and wastewater, they have G43009 for critical infrastructure CIP. These are sector-specific guidelines for cyber-related standards. For us, we are interested only, ANSI ISA 62443, because the process industry is focused in this presentation. So how to address these standards? Standards are typically, many people think, standards are kind of like a, give you like a direct way on how to address them, but they're actually not prescriptive. Many of the standards are not really prescriptive. They give guidelines and recommendations. It's up to the user on how to implement them. So, and also remember, we're talking about safety and security. We're not talking about like in OSHA standard, like any electrical safety. There could be very prescriptive, but here these standards, safety and security, are not really they're not prescriptive. They give good guidelines, good recommendations on how to address it. It's up to the user to understand and how to implement it. And standards are not necessarily laws. Remember, also we're not talking about OSHA and NEC here. These functional safety and security standards are not necessarily laws, but they carry a certain level of certainty. In case something happens, like somebody accidentally died or something, some accident happened. So these are not laws, but in court of law, they will definitely take these standards into a higher certainty and consider them with a high degree of validity. So standards and guidelines are only as good as implemented. So these are not really prescriptive, so it makes it a little challenging to the user on how to address them. So it's the user's responsibility to understand completely and do their best to address it. So how to get a certification for the components used in our functional safety and cybersecurity? There are some accredited functional safety certification bodies like XCDA, TUV. They give certifications for functional safety. Few accredited ISC security certification bodies for security are Open Process Automation Forum, Bureau Veritas, and XCDA. These are the security accredited bodies. So now, if you look at a clause 5.2, 5.2, it specifically says vendor to have their own functional safety management plan. Any of your vendor claims functional safety for their equipment. That means if you're using a functionally certified component from your vendor, they need to have their own functional safety management process. So no one can claim a functional safety certification without having any functional safety management from their side. As an asset owner and the end user, you should have your own functional safety management. If your vendors have their own FSM, do not mean that directly applicable to you. You should have your own FSM. And in the clause 5.2 there says FSM personnel who are working on the safety instrument design must be competent. This is highlighted in the recent standards since 2016. So that means you who are working on this design must be very well versed in what they're doing. So that do not mean that the competency need to be trained by external. The person can be trained either external or internal training, but that need to be documented. So that means the person who are working in these designs must be very well versed and internally certified or either externally certified. So the competence is very much highlighted in the newer standards, and it need to be documented. If you do not document this one, then you're not really meeting your FSM functional safety management process per their standard. So who is responsible? Who is actually responsible for implementing the standard? The standards do not really specify who is responsible, but in my view, the end user have more responsibility to meet the standards. Your vendor may claim something, but it is your responsibility to make sure whatever these claims are correct. Because at the end, your employees and your personnel are at risk. So in my view, the end users should be completely responsible on meeting the standards. Because it's their backyard, it's their basement. So vendor may claim some things, but make sure he's right. The functional safety can be achieved by meeting and maintaining SIL target levels, which are 1 to 4. These are safety integrity levels from 1 to 4. These are assigned in ISA 61151. So SIL, what is SIL? SIL is a measurement of system performance regarding the probability of failure in demand. In the process industry, we actually use only PFD average. There is something called PFH, probabilities failure per hour, but which is rarely used in our process industries. This PFH normally used in a machine sector, machine industries. So what is PFD average? Now, so safety integrity levels are defined from 1 to 4. Now that means the probability of demand, probability of failure on demand belongs to these numbers here. So, and risk reduction factor is defined as 1 by PFD average. That means whatever the risk reduction factor you're claiming is 1 1 divided by PFD average of these numbers. So that means SIL1 means you can claim a risk reduction between 10 to 100. You can claim the risk reduction between 1 to 100. If it is a SIL2, it should be 100 to 1000. That's the risk reduction you can claim. Is a safety PLC mandatory? In standards, they do not really call for safety PLC. It is not really mandatory to use it. It depends on how your safety assessment comes up with different recommendations. So in some cases, based on the design of your processes and available instrumentation and how you implement the controls, you may not need even SIS, because BPCS, when you're using a BPCS, basic process control systems, you can claim a 0.1 risk reduction. So if your risk assessment says 0.1 is enough for the whole your process, then you don't necessarily need a SIS. But you need to perform functional safety management process before concluding, you just need only 0.1 risk reduction. So as I said, it's not mandatory to use a safety PLC, but the safety system also, if you ends up with a safety system through your risk management, you can also do a hardwire wiring design. It's not mandatory that safety PLC is required. So IEC 6151-1 clause 3.2.67 says SIS may include a software. We do not really mandatorily say, hey, you need a software to achieve to meet the standard. So this means you can use a sensor and you can use simply hardwiring design with the relays and everything. You can still meet the standard as long as you make sure you're meeting the risk reduction. But the problem with the hardwiring design is, it usually brings up a complex wiring. That if you use just the sensors and relays, there are too many wires going on here and there, and then it's very hard to troubleshoot. And it's also a little cumbersome to design in the first place. So if you use a safety PLC, it makes things a little easier, because you have instruments and the PLCs have good diagnostics. So it makes things a lot easier if you prefer to use a safety PLC, but it's not mandatory. And also, if you use a smart instruments, with the hot diagnostics, you can get a lot of diagnostic out of the instrument and then use that as a predictive maintenance and use this for data collection methods and increase your plant reliability. So as you can see now, it's preferred to use smart instruments, but it's not really mandatory to use any of the smart instrument. You can still meet the standard, using a hardwire design also, but it brings a lot of complex wiring into your plant. Is SIS just enough? Once you perform your functional safety management, then if you come up with a SIS, is just enough? No, it is not enough, because we already seen in the last slides, to meet the standard, you need to perform a cyber safety assessment. Simply having SIS do not mean that you're protected from any of the cyber security attacks. So because attacks can happen also on the safety instrument system itself. Also, not having an SIS system do not mean cyber safety is not required, as BPC's independent protection layers can get compromised and then compromise the safety of the plant. Because we already, when we're doing the functional safety assessment, we already claim a BPCS risk reduction for 0.1. So if you don't properly perform a security check on BPCS, that could also affect the risk reduction factor that you already claimed. So that means having not having a safe system does not mean that you don't perform any cyber risk assessment on your control system. So how to achieve SIL? SIL is basically depends on these three processes here. One is the failure data and three components here, and one is the systematic capability, and another one is the architectural constraints. When these three components are integrated together, and then only you can achieve a proper safety integrated level. We'll look into these two components below. Now, what is the systematic capability? Systematic integrated level and failure data are highlighted in the certification by the accredited bodies. If you see any EXIDA or a TUV safety certification, they specify the systematic capability. That means, like a SIL 2, SIL 3. It's also called a SC. If any component is SIL 3, that means you can use that component anything below SIL 3 level. You cannot use it for higher than what is specified on the certification. Like if any component specified as a SIL 2, you cannot use it on SIL 3. You can use it only SIL 2 or below. So the other component there, the architectural constraints. So architectural constraints also known as a voting methods. What are voting methods? Classic voting methods are 1 of 1, 1 of 2, 2 of 2, and 2 of 3. So that means one sensor is failure is taken into account for the risk reduction. Here in 1 of 2, we have 2 sensors, but one of them is considered for safety risk reduction. And there's other voting methods are available, which are called diagnostic based methods, which are 1 of 1D, 1 of 2D, and 2 of 3D. So D here means the diagnostics. You're taking advantage of diagnostics in this method. In classic voting methods, we're not taking advantage of any diagnostics. We'll see how in next slides how we can properly use the diagnostics. This is a very interesting one there. Why we need diagnostics? Because diagnostics can improve safe and reliability of the fail-safe circuit. Diagnostics normally achieved through a HOT system. But HOT is not a safety system. So that means whatever the information you get on your HOT system, you can use it for diagnostics, but you can't use it for in a safety circuit. So if you don't have a HOT system, what you can do, you have a smart instrument of 4 to 20 milliampere, but you don't have really a big asset management system. So what you can do there, you can still take an advantage of the diagnostics from the instrument. So how we can achieve it? There is something called a NAMUR NE43 recommendations. So in a normal 4 to 20 milliampere instrument, the normal operation, as we know, it's between 4 to 20 milliampere. But if you configure your instrument per NAMUR NE43 recommendations, you can have these extra features here. For 3. There are three. There are two on the lower side and the 2 on the higher side. So whenever, if any calibrated instrument, if any correctly working instrument, it should not go beyond 4 to 20 milliampere, right? It should be always be 4 to 20 milliampere because the instrument is accurate and working correctly. If it is ever going beyond 3.8 milliampere. That means the instrument is actually, out of calibrated range for whatever reason. It could be a drift, or or it could be a clogged impulse line. So it is drifting. So that means there's something wrong with the not really with the instrument, but something with the process, or it could be also an instrument, because it could be also a drift. So you can take advantage of these two values as a part of your diagnostics, and can still achieve one of 1D or 2D votings, even if you don't have a hot system. So how to use the diagnostic methods for 2D? Suppose you don't have now a hot system. Let's look into an example here. So you have 2D architectural constraints voting methods. That means you have two instruments, and you are making sure one of them is working correctly. So the diagnostics are monitored all the time using this method above. You look for these two values from the higher side and lower side and see what's happening. If the instrument is working correctly and the process is right, there should not be any deviation between 4 to 20 milliamp. It should be working very nicely and correctly. If it is ever deviating into these values, that means there is something wrong. So that's what we're trying to do here, to take advantage of those diagnostics. So the diagnostics are continuously monitored in the PLC program. You can program the PLC to look for these two values, 3.8 milliampere and 20.5 milliampere. So if anytime the program sees, hey, the instrument is giving 3.8 milliampere, or it is deviating from 4 to 4 milliampere, or from other side, it's deviating from 20 milliampere. So that means there's something wrong. So we can program that in the PLC and see if you see an error there. What you do, you degrade it to 1 devoting now, and put it in an automatic mode. And then you still monitor the diagnostics. You keep monitoring it. You don't want to lose the diagnostics there. So once it is degraded to 1 voting, document that error and caution the operator, saying, hey, there is something wrong with this instrument, like an HMI alarm or something. Just warn him there's only one instrument working now, and the other one is has some problem. So the diagnostics are still monitored for 1 voting, and now you have something called a mean time to repair time. So during that time, you have within that time, the problem need to be fixed for the second instruments. This MTTR time is it comes from when you're making the SIL calculations. That's when you give the inputs for the calculation, saying, hey, this is my mean time to repair. That means I'm gonna fix this instrument between this time, within like 72 hours, or like 2 days, 48 hours. So if it is fixed, then we'll go back to 2D voting. Using manually operational selection again, go back to 2D voting. If it is not fixed during that time, that means your SIL calculations, or the SIL risk reduction factor, whatever you have taken during the SIL assessment, that because that do not meet the MTTR time now. So the plant need to trip the plant and then document the error. You could not fix it within the mean time to repair time. And that's where your SIL risk reduction factor comes. So during 1D voting, if any error is observed, what you do? The plant should trip because you have now no protection for your plant for a fail-safe action. So that means during 1 of 2D voting, if any error is observed, it goes to 1 of 1D, a still diagnostic monitor, and then that and another instrument is also now showing some kind of error, then you trip the plant should go to the safe mode. So now how you can use these diagnostics in 2 of 3D voting. Now it's the same philosophy that you keep monitoring the diagnostic for these 3 instruments. And for 1 of the instrument there is an error, then you go to 1 of 2D voting. Now the same steps here, you document the error and say there is something wrong with the instrument, which we need to look into it. And then caution the operator a degradation of the voting methods happened. The architectural constraints now went to a little lower. The degradation happened, and mean time to repair time is running. This could be an alarm. You can put on a HMI alarm saying, hey, the MTTR time is running now. Go and fix the instrument or take what are the actions required to fix the instrument. But you still want the diagnostic for the rest of them, 1 of 2D here. And if you see error for any of the 1 of 2 instruments now, then the plant should go to a safe mode, because now you don't have any protection against the plant. Because during the seal calculations, you decided, we need 2 instruments to be to keep the plant safe. So that's why even it's in 1 of 2D voting now, you will go to the plant goes to safe mode, because now it becomes 1 of 1 voting here. If you see any error in 1 of 2D, so that means you don't have 2 instruments which you concluded during your seal calculations. That's the minimum requirement to keep the plant safe. So the plant and the issue is fixed within this mean time to repair time. Then plant, and then it goes back to 2 of 3D voting, and then as usual the plant runs nicely. If the issue is not fixed, then plant should go to trip, and then plant the trip is shown as green because it's assumed that you have done a proper functional safety management, and it goes to fail-safe mode. It's not really a danger, but it should be going to a safe mode, fail-safe mode. So now during seal assessment, if you have more than, if you end up with a seal 3 targets, what you can do, seal 3 targets very hard to achieve because it needs a frequent testing. So that's why you can bring up a partial stroke testing method. It's a different method. It's a very different method than the 1 of 2 for seal 2 and seal 1. But the partial stroke testing, it brings up like a complex design changes, like you need new bypass lines within the testing, and and a very complex partial stroke testing equipment. So if you end up seal 3 during your seal assessment, you better consider other protection layers to bring it down to seal 2 or seal 1, because seal 3 is very hard to achieve because it needs very frequent testing. One of the reasons you could end up in seal 3, because if you're high turnaround time, that means you don't want to stop your plant for 4 years. In one of my old companies, they didn't want to shut down the plant for 4 years. That means you cannot test any of the functional safety equipment for 4 years. So that makes it very difficult. And that's when you could end up on a seal 3 level targets. So in partial stroke testing, analog positional feedback is necessary. We'll see why here. So what is the partial stroke testing overview? It basically monitors the valve movement. Not a complete closure, but it just observes if the valve is moving properly. So it's not stuck up. So that's the main point of checking partial stroke testing. So normally you initiate the partial stroke testing, whether it could be auto, you can program it, or you can do a manual also. That means on a certain specific time you want to execute this test, like 6 months down the line on this date you want to execute this test, you can program it, or you can also manually execute partial stroke testing. So in this partial stroke testing, the valve observes, the program observes that the valve is ready. If it is, that means is there any interlock stopping it and moving this valve a little bit, that all you need to program it in your PCS. If the valve is not ready, then test is inhibit, and then you check what is the next procedure on why test is inhibited. If the valve is ready, then valve stroke is initiated. Not a full stroke; it's just only very partial movement of the valve, and the valve movement is measured. When valve movement reached the PST set point within the expected time interval, that means your partial stroke testing is successful. The PST set point, you need to be careful in defining how much turn you want to turn the valve during the actual process is running, right? So these things you should take care when you are designing your whole system. If it ever fails, if the valve did not even move to the set point that you want to move in, like 2%, 3%, sometimes it will be also 10% of the valve design. If you did not move with that far, that means test is failed. So that means you need to find out now why it did not move to the set point. There is something wrong. So that means when actual demand happens on the valve to close the valve, the valve may not close completely. So the test is actually failed if you do not reach the set point within the test interval that you already defined in your the program. So that's about a little bit of the functional safety there. Now we'll see how to address cyber standards. Cybersecurity, standards and set best practices. As I said, it's all qualitative. Not really prescriptive. They don't tell you exactly, do this one and you're good. So ANSI IC 62443 is a very good standard. Very well written, very easy to understand. And then they assigned a security assurance levels 0 to 4 there in the standard, which is something similar to like our functional safety SIL levels. Much similar, not really exactly the same, because in the SIL levels, what is the probability of failure on demand, and the risk reduction you can get out of it. But in security assurance level, these are all qualitatively assigned. That means there is no numbers around it. We'll see in next slide why we could not assign numbers there. So these are all qualitative words there. So that means it could be low, medium, or high. So that means your security assurance level is low, your security assurance is medium, your security assurance level is high. That's how these are defined in IEC 62443 standard. There are no numbers assigned to it, so you can simply see, hey, this is my risk reduction, and then I made it, and then I'm good. That's not how it works in the security standards here. So security levels are SAL 1 means protection against a casual coincidental violation. SAL2 means protection against intentional violation using simple means. SAL3 protection against intentional act or violation using sophisticated means. And SAL4 is protection against intentional act or violation using the sophisticated means with very extended resources. This is how the security levels are defined in a 6443 standard. SAL 0 means there is no requirement. Initially, when they developed 6443, there was no SAL 0, but later they also bring this one in. They see the necessity of having, a few times you may not need any requirement, maybe it's completely isolated, for some of that reason they brought it to SAL 0 now. So how to address cyber standards? So security assurance levels depends on 7 factors defined in the standards, which are called foundational requirements. These 7 factors for SAL are access control, use control, data integrity, data confidentiality, restricted data flow, timely response to event, and resource availability. IEC 62443-3-3 Annex B shows very detailed breakdown on what are these foundational requirements and how they're actually mapped to each security assurance level. It's very detailed out, very nicely done. You can clearly see, you don't even need to know much about the ICS security. Even if you look at this Annex B, it clearly tells you the mapping between the foundational requirements and how you can achieve SAL level there. So top security vulnerabilities for ICS, are inadequate policies or procedures. Now, this is a mostly big issue in security, ICS security. Inappropriate remote access controls and improper software maintenance and failure to observe any inappropriate activity in the system. So there is one method called defense in depth for cyber security standards. Okay, so now we looked at in the last slide. We looked at what are the top security vulnerabilities? Policies and procedures, inappropriate remote access controls. But erroneous actions are being the least of the threats. So what do you guys think? Out of all these security vulnerabilities, these erroneous actions are the least of the threats. It feels like, right? It feels like, erroneous actions are not much of a big of a threat, because security means we have to worry about, cyber security coming out of the plant. It's not really erroneous actions, but we all know what happened, how Stuxnet happened, but not many people know how, the details about it. If anybody know Stuxnet and what happened there?
Yeah, and I was just trying to open everybody's mics, Sunil. Yeah, Stuxnet for sure. So, well, Sunil, please go ahead. I'm going to see if I can open up the mics for everybody.
Okay. Yeah, Stuxnet, people who don't know about it, this attack happened on Iranian nuclear plant, and that happened because of a USB, somebody put a wrong USB stick in one of the engineering stations. But not many people know how that USB stick got there. First of all, how that USB stick, got into the plant. You don't see that in internet, but what actually happened was, whatever their adversary, they keep dropping USB sticks around the plant. So, but you don't find that in internet, but that's what actually happened. They just dropped a couple of USB sticks around the plant. Hopefully, somebody take a bite on it, and then they took that. Some employee took it, and curious, it's very curious that you found something outside of the plant. It could be yours, or it could be someone's. You don't know. It's very curious that you find something, you want to look into it. So that was a perfect bite, and that's a great example for how Erasmus actions are not being a list of the threats, but is one of the higher threat. So that employee took that USB stick and then curious about it and put it in the link station, and then that's how it got attacked. It's I don't think you find this on the internet, and I wish I could have I stored the source or read about it, and that totally made sense to me, because there's a perfect bite that you can do, instead of trying to break all the network securities or physical boundaries. Is a very, very good bite for anybody to do some security attacks. So how to address cyber standards? There's you might have seen a different types of defense in depth, but I like this version. For me, it feels like it's mostly it is comprehensively done here. Defense in depth normally shown in a different circles, inner circles and outer circles, like that. For me, it feels like if I look at that particular drawing, for me it feels you need to break the outer circle to get into the inner circle, but that's not the case. It needs to be protected through all of them as an integrated approach, not the way it is shown in a typical defense in depth drawings. You need not break the physical security to get into ICS. You could break network security, or you could do a wrong policy and procedures approach, and then you still break the security of ICS system. That's why I draw this one, as a integrated approach. That means ICS is protected only when you actually address each of these three components here. So another point inside how to address these standards still is quantifiable, as we saw in the other slide. You can simply know which sale and what's the risk reduction you can get after the sale. But the security assurance level is not quantifiable yet. I mean, it may be possible in future they could quantify it. That means what is the security assurance level? So one means you could achieve this risk reduction, then you met your assurance level. But it's very difficult. The reason is if you see cyber risk definition, which is threat, vulnerability, and consequence. It's very hard to put a number on threats, because threats keep changing, and most of the threats are, they have intentions, and how you put a number on an intention, so that's why it is very difficult to give a numbers for security assurance level. As of now, these are only qualitatively assigned. That means low, medium, and high, but not really. You don't have like a direct numbers assigned there. In future, maybe it is possible that all different industries come together and then agree on proper modeling methods, and then when the data is available, and then it may be possible, but I don't think it is possible. I don't think it's possible ever. I could be wrong, but I don't think it's possible ever, because the threats keep changing and the intentions have to keep changing. Maybe an example is like somebody amateur guy try to just mess around. How do you put a number for that? How do you put a number around some amateur guy in some other country trying to mess with it? You can't put a number around it. So I don't think it's possible ever to put a numbers for security assurance levels. But it is a hope that in standards there are standards also to specified now. No, they might do in the future, but let's see. So stars are assigned to qualitative words like low, medium, and high. So what they mean for as an asset one, this is very challenging. This is very challenging to define them and what it means to you. But you, as an asset one, you need to define to suit your application and then find out how assign them. There are no really clear guidelines as there. All you have the recommendations, and then kind of like on your own now. Um, if you really need a help on how to define them, like any SSR, like an external party, like an example, like an Exida or somebody, they can help you in converting them to a quantitative levels. What this mean by low, medium, and high. They can help you and converting them to qualitative words to quantitative. For a quantitative approach, a risk graph or risk matrix are very good tools. These are a qualitative approach. You can use these risk graph techniques and risk matrix techniques to assign properly. Companies can, you can, if you already have a process functional safety risk graph, then our matrix, you can take that one and use as a fundamental basis to convert for your cybersecurity risk graph or risk matrix. That should be a first basis. It gives a good base for you, to start with it and then work with the SSR, the accredited SSR to convert it properly. They will discuss with all the stakeholders in the company and decide how to adjust or assign it properly. So how you keep up with the cyber threats? This is very crucial for a security point of view. You need to know what's happening. In functional safety world, you don't need to really know on day-to-day basis what is happening. Probably have the data, what's the failure data, the capability of the instrument, and your voting method. So there's nothing really to keep up with what's happening every day to the instrument. But here, that's not with the cyber threats. You need to really focus and you need to pay attention what's happening because it could happen to you. So these are very good sources to keep up the threats on what's happening. CISA got a cybersecurity infrastructure security agency and ARC advisory group. ICS CERT, ICS CRT is also industrial control system cyber emergency response team. They have very good postings there, and then they keep up with the threats, what's happening around the world. And there is actually a very good one, RASCS. It is called a repository industrial security incident. Yeah. They're very good. They're very good, but I don't know what's the reason behind it. They really stopped posting. I still see their old website, 2015 or 2016. They stopped posting about it. The thing I liked about them was, they have very good report of the incident, and they have very good report, and that's I liked about them. But unfortunately, not sure why, but they stopped it. They stopped posting about anything since 2016. You can still, this website is still alive. You can open it and see and how good they were at the time. The other one I like is security. This particular link, securityweek.com. These guys seems to be keeping up the threats very frequently than the other ones shown here. Like you can see weekly basis, very quickly they're updating what are the threats. That's why I like this one, securityweek.com. So another best source for cyber threats, is a manufacturer announcement and news. why that is, why we can't wait until it comes out to the public. Why? Because most of the attacks happen in cybersecurity are zero-day exploits. That means you don't know, the public do not know. The vulnerability is not known to the public yet. That's most of the attacks happens on zero-day exploits. So what if something is wrong with the plant? The first thing usually the asset owner or the operator try to get a contact with the manufacturer. It's easier. Hey, there is something wrong with my the PLC, whatever, there's something going on. So that's why another best source is manufacturer announcement and news, and then they would come to know from the because somebody contacted them. Hey, there is something wrong with the PLC. Please look into it. So there's also another best source now. So keep up with your manufacturers. Keep looking for the news. Maybe sign up for the newsletter or something. So that would be a nice source there. So we need to bring a safety approach also to cyber. That means cyber timely response to an event. Keep a cyber emergency response plan in the control room. I have seen a safety response plan. Hey, there's some fire happens, do this one. Or some accident happen, do this one. But I rarely seen a cyber emergency plan in the control room. Like means a cyber attack happened or you suspected something happened, you need to have some kind of action or like call the ICS security guy, or some take these actions. So some kind of emergency response plan is required in my view. It should be posted in your control room along with normal OSHA pamphlets. The same way that you treat the electrical safety and the process safety, you should treat the cyber security threats also the same way. That means you want to keep an emergency response plan in the control room. Resource availabilities. This is like a mean time to repair that we have seen in in functional safety. It's like keeping keeping the backup systems. It's all like spare. Like a 1 of 2 voting, you can say similar to that. So you need to keep up your backups and equipment inventory as a part of the incident response plan. And cyber recovery plan. So once your attack happened, you need to properly recover it. You need to have a proper recovery plan. So that means it should be documented, properly, saying hey, these are the actions we're going to take in case of our system goes down because of cybersecurity. So a proper recovery plan is very much necessary. And what you personnel should play a critical role in developing the recovery plans, as IT personnel typically do not have functional knowledge of ICS installations. So in my suggestion is assign one person in your controls team as a subject matter expert, for cybersecurity, and either train him externally or keep him, or internally if you have availability, and keep that person as a subject matter expert to help with IT team, to integrate properly these security aspects.
Hey, Sunil, we're running up on time here. If we're getting
okay, it's all over.
Ah, I set you up perfect.
Yeah, it's just perfect. So 100% safety and security. Ones must maintain as it was proper test records and maintenance procedures as ICS safety. Also security is a life cycle until the project decommissioning. You need to keep the procedures and test records until the project decommissioning. It's a total life cycle. We cannot, once you install the plant, it's not done. It need to be total life cycle. So finally, we all know it's impossible to achieve 100% safety and security, but we try our best to get it done. So that's all from my side.
Wow, that was
Hopefully-
really comprehensive. Thank you, Sunil. That's
Yeah.
it's quite a lot to carry in an hour and
Yes.
change of presentations. So take a breath, grab a drink if you need
Yeah,
to. We'll
yeah.
I know we'll have some questions from the audience. I'll just share a story.